Hey everybody, welcome back. This video will cover going over the April 2021 Solutions Quarterly Practice Quiz Review. So the topics that are covered in this video, or the questions that are covered in this video, come from properties of water, solubility factors, concentration part 1, concentration part 2, but only ppm. So if you need refreshers on any of these topics, those are the videos that these come from. So again, we're going to go over question by question of the Unit 7, so Solutions Practice Quarterly. Okay, number 1, it says in an aqueous solution of potassium chloride, the solute is, remember, we have solute plus solvent, and that gives us a solution. So the solute gets dissolved, the solvent does the dissolving, and the solution is the mix between the two. So generally speaking, when you see aqueous solutions, that means something dissolved in water. So in this case, water is going to be our solvent, and whatever dissolved in that water is our solute, and that is potassium chloride, which is KCl, making it answer choice C. Number 2, this is as the pressure of a gas confined above a liquid increases, the solubility of the gas in the liquid blank. So we're talking about pressure and we're talking about solubility of a gas. So for gases, and pressure only really affects gases. So first, pressure affects gases only. And so when you increase that pressure, you are actually also increasing that gas solubility. So the more likely it is to be dissolved. And when you decrease that pressure, the gas solubility goes down and that gas wants to leave. So if you think about a can of soda has a bunch of carbon dioxide dissolved into the soda. It's under a very high pressure. So the gas is very soluble in that can. But as soon as you open that can, decrease that pressure, bubbles start coming up. And so when you see bubbles, that means the gas wants out. It is no longer soluble. So according to the question, we want to increase the solubility of the gas. So we're going to increase the pressure. Number 3 is very similar. At room temperature, the solubility of which solute in water would be most affected by the change in pressure. So again, we're changing pressure. This only really affects gases. So your next question is, well, which one of these answer choices is a gas at room temperature? And that is carbon dioxide. Okay, number 4, continuing with this kind of topic. Given the diagram below, that shows carbon dioxide in an equilibrium system at temperature 298 K and a pressure 1 atm. So all this stuff right here is there to confuse you. All it's saying is what changes must increase the solubility of carbon dioxide. So if you want to increase the gas solubility, we talked about we have to increase that pressure. So we can get rid of answer choices C and D. And then if we're talking about temperature, so we still want to increase that gas solubility. Think about a can of soda. What has more bubbles in it? So every time you sip, you have more bubbles, cold soda or warm soda. So you should think cold soda. So you want to decrease that temperature. The colder something is, the more soluble or the more gas that is dissolved. So if you take a sip of cold soda, you get every sip you have a bunch of bubbles because the temperature inside your mouth is a lot warmer, so the gas leaves. But the cold soda has more bubbles in it. If you've ever drinking warm flat soda, there's no bubbles whatsoever because all of the gas left. So we want to increase pressure and decrease temperature, and that is answer choice A. Number 5, the solubility of a salt in a given volume of water depends primarily. So again, we're talking about the solubility. And solubility is the amount of stuff that can be dissolved. can be dissolved. And so one of these four things affects how much can be dissolved, and the other three affects how fast something dissolves. So the speed at which something dissolves is not the same as amount of stuff that can be dissolved. That can be dissolved. So the amount of stuff that can be dissolved again is solubility, and the speed of something that speeds up the rate of reaction. So of these four choices, the surface area speeds it up, does not change the amount, so it can't be A. Temperature affects the actual solubility or the amount. So if you think of hot coffee and iced coffee, if you get iced coffee, generally you have a big chunk of sugar on the bottom. Hot coffee, same amount of sugar, no lump of sugar on the bottom, because things become more soluble at high temperatures. So solids become more soluble at high temperatures. The rate at which they're stirred, again, that affects the rate of dissolving, not the amount. And pressure on the surface of the water. Pressure only really works if you're trying to dissolve gases. If you're dissolving salt, salt is a solid, so pressure does not work. Meaning the only logical choice here is B. Okay, number 6. We're going to jump into some calculation questions now. What is the molarity of 1.5 liters of an aqueous solution that contains 52 grams of lithium fluoride? And it gave you the gram formula mass. So the molarity formula is on your reference table, and it is, so molarity is big M, moles of solute, so the thing that gets dissolved, over liters of solution, so the entire thing. And so you can also use the molarity triangle, so molarity is big M, moles of solute is N, lowercase n, and liters of solution is L. So that's the molarity triangle. And so whenever you have a formula, your first step should be to list out what you know and what you don't know. So we have N, we have M, we have L. So what is the molarity? So we're looking for capital M of 1.5 liters, 1.5 liters that contain 52 grams of LiF. Now, right now we have two unknowns. We don't have the number of moles, but we're also asked for molarity. So if you're not given everything in this formula, in the equation, you're going to have to do something else. What we're given, though, is 52 grams of LiF. So what we need to do, we need to convert this to moles, then use equation. So we have to find N before we can use the molarity equation. And so when you're converting from grams to moles, we're going to use dimensional analysis. You have your 52 grams over 1. You want grams to cancel, so it goes on the bottom, and moles goes on top because we're looking at it. And so 1 mole, that will always be your given. And in that blue box, that is going to be the molar mass of our compound. And so this question gave it to us. It says the molar mass, or formula mass means the same thing, 26 grams. So it's saying if you have 1 mole of LiF, that's 26 grams. We have 52 grams, so how many moles is that? So grams cancel out. You're left with 52 over 26, which gives you 2. And again, your unit is moles. And so you're not done there. That's your unit, that's your mole, your little n. So now we have all that we need to finally go back and use the molarity triangle. So whatever you're looking for, you're going to kind of cross out. So molarity is moles over liters. So you have 2.0 moles over 1.5 liters. 2.0 divided by 1.5 is 1.3, and then moles divided by liters is moles over liters, and that's the same thing as molar. So big M, unit-wise, is the same as moles over liters, making A our answer. Okay, number 7 is another molarity question. So again, let's add our molarity triangle. moles, liters. If you like plugging into the equation and going that way, that totally works as well. So we have our N, we have our M, we have our L. What's the concentration of an aqueous solution that contains 1.5 moles? So 1.5 in 500 milliliters of solution. Now our problem here is this. So L is liters of solution, but we're given milliliters. So fun fact, 1000 milliliters is 1 liter. So all you have to do is just move that decimal point over 3 spots to make it 0.5 liters. So now we have everything we need for our equation. We're looking for molarity, so big M. Cross that out. M is N over L. So our N is 1.5 mole. Our liters is 0.5. 1.5 divided by 0.5 is 3. Moles over liters is moles over liters. And again, you can write that as 3M, which is answer choice C. Okay, number 8, what is the molarity of the solution that contains 0.5 moles KNO3 dissolved in 0.5 liters of solution? Again, our molarity triangle, molarity, moles over liters. So we have N, we have M, we have L. What is the molarity? So if it says molarity, if it says concentration, we're looking for that. 0.5 moles, 0.5 mole, 0.5 liters, that goes there. So again, we're looking for molarity. So M is moles over liters. M is 0.5 mole over 0.500 liters. 0.5 divided by 0.5 is 1. Moles divided by liters is moles over liters. Or you can write it as 1 molar, which is answer choice A. Okay, number 9 is more of a definition question. It says the molarity of an aqueous solution of NaCl is defined by the, so it's the equation but in words. So molarity, again, from the back of your reference table, is moles of solute over liters of solution. So remember, solution is what you dissolved plus the water. So both those things, your entire picture. So we're looking for moles, so we can get rid of A and B. Per liter of water or per liter of solution. Again, solution is that whole thing. It's going to be D. Moles per liter of solution. Number 10 is very, very similar. Which phrase describes the molarity of a solution? Again, molarity is moles over liters. And so, we know it's moles. Now it's moles of solute. So the thing that gets dissolved, making it C. Again, formula is on the back of the reference table. Number 11, which unit can be used to express solution concentration? So J is joules. We haven't talked about that. Not going to be that. Liters per mole. It's using the right units, but in the wrong way. So remember, again, molarity is moles over liters. So moles over liters is a bad color. Moles over liters. So that's backwards. If you look at D, moles per second, that does not make sense. That is not the answer. So again, it has to be C, moles over liters. Again, the formula is on the reference table. Look at the formula. Okay, number 12, last one, very kind of conceptual. At A, 3 molar HCl solution contains a total of, so again, molarity is moles of solute over liters of solution. So again, we're talking about moles, so it has to be A. It can't be A, it can't be B, with that little update. So moles of HCl, again, the second part of the equation, liters of solution, which makes it C. Moles per liter of solution. Okay, number 13. what is the molarity? So again, we're going to use our molarity triangle. Molarity, moles over liters. N, M, L. What is the molarity? So we're looking for that. Containing 20 grams of NaOH and 500 milliliters. So this is the hardest possible molarity question you will ever see. So your first thing should be to convert the milliliters to liters, so 0.5 liters. And now we need to convert this 20 grams to mole. So we have 20 grams over 1 mole in grams. And so in this blue box is the molar mass of NaOH. But unlike the previous question, it was not given to you, so we need to find it. So we have Na, O, and H. The mass of Na, according to the periodic table, is 23. And we have one of them. One oxygen, the mass is 16. You have one H, the mass is 1. So 23 plus 16 plus 1 is 40 grams per mole. And so that 40 goes there. So that's where that came from. And so grams cancel out. 20 divided by 40 is 0.5 moles. And so now that is our N. So now we have everything we need to use the molarity equation. Molarity is moles over liters, so 0.5 mole over 0.5 liters. 0.5 divided by 0.5 is 1. Moles over liters is moles over liters, which is the same as 1m, which is answer choice A. So again, that made you convert to moles without the molar mass and made you change the solution unit, but that is it. Okay, number 14, which solution is the most concentrated? So concentration, again, measures the amount of stuff that is dissolved. So if it's the most concentrated, you want the most stuff in the least amount of solution. So if you're thinking about making lemonade, if you're making really concentrated lemonade, you have 1 cup and you put 5 scoops of lemonade in it. That's very concentrated. You have a lot of stuff dissolved in a very small amount of volume. If you use that same 5 scoops, but say in 5 cups, you've now spread that out more. So you want the most amount of stuff in the least amount of volume. And so the most stuff in the least volume, that is answer choice D. Number 15 says, what is the concentration of AgCl in an aqueous solution that contains 1.2 times 10 to the negative 3 grams of NaCl in 800 grams of solution? So when you have these little numbers, and we know from the answer traces, we're going to use ppm. So ppm is another equation on the back of your reference table. It is the mass of your solute. So again, what's being dissolved? The mass of your solution. So that's, you can call this your part. This is your whole. Times 10 to the 6, which is the same as 1 million. So I like to write it out as, our solute, our solution, and then we're looking for ppm, or the concentration. So again, concentration is ppm. So we're given 1.2 times 10 to the negative 3 grams of what we're being dissolved in 800 grams of solution. So then it's just 1.2 times 10 to the negative 3 over 800 times 10 to the 6th. Now, if you're plugging this into your calculator, you need parentheses around that scientific notation. And so when you plug that all in, you should get, and again, I like to do this divided by that, hit enter, then times by 10 to the 6th, and you get 1.5 ppm, which is answer choice B. Again, one of the hardest parts of these questions is properly plugging it into your calculator. Number 16, parts per million is used to express the, again, parts per million is a unit to describe concentration, the amount of stuff dissolved in solution, making it B. Okay, Number 17, what is the total mass of solute in 1,000 grams of solution that has a concentration of 5 parts per million? So this question is a little bit more complicated. We have our solute, so the amount of stuff being dissolved, that is our X, or what we're looking for. Our solution, we know, is 1,000, and our ppm is 5. So what we need to do, again, ppm is mass of solute over mass solution times 10 to the 6th. So if we plug in what we have 5 equals x over 1,000 times 10 to the 6th. So we need to find that x. So what you need to do is multiply both sides by 1,000 to get rid of this. So 5 times 1,000 is 5,000 equals x times 10 to the 6th. Divide both sides by 10 to the 6th. 5,000 divided by 1 million is 0.005 grams, which is answer choice A. And that's it. Number 18, if 0.025 grams of PbNO32 is dissolved in 100 grams of H2O, what is the concentration or resulting solution in parts per million? So it's telling you we're looking for parts per million, but our problem, we were given the solute, so the amount of stuff that was dissolved. We were given the solvent, the amount of water, so 100 grams, and we have to find the solution. So remember, this is your part, this is a part, and this is your whole. Generally, we don't use this part in the equation. We need to add those two up to make the whole. So 100 plus 0.025 is 100.025. Okay, so now we have everything we need. We're going to do our solute, so 0.025 divided by 100.025. Again, in this specific question, if you forget to do that, not the end of the world, but there are other questions where it is very, very important that you do that. When you plug all this in, you get 249.9 blah, 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 blah. If we're using significant figures, that is 250 significant ppm, which is answer choice C. Number 19, how many grams of KOH should be dissolved in water to make 200 grams of a 10 ppm solution? So again, very similar to the other question. We're looking for the solute. We have the solution, which is 2,000, and our ppm, which is 10. And so if we plug that in, we get 10 equals x over 2,000 times 10 to the 6th. And so we're looking for that x. Our first step is going to be to multiply both sides by 2,000. And so I'm going to bring this up here. We get 20,000 equals x times 10 to the 6th. To get x by itself, divide by 10 to the 6th, divide by 10 to the 6th. 20,000 divided by 1 million, or 10 to the 6th, is 0.02. Now, the problem is we don't see that answer. We see 2 times 10 to the negative 1, 2 times 2 to the negative 2, 2 times 2 to the negative, 2 times 10 to the negative 3. And so we need to convert this to scientific notation. It's going to be 2 times 10. And again, if you have a negative exponent, that means you have a decimal. But we moved it 2 spots, so negative 2. So 2 times 10 to the negative 2, you're moving that decimal point 1 spot, 2 spot to get answer choice C. Okay, and the last one, number 20, what is the concentration expressed in parts per million of a solution containing 20 grams of sugar and 80 grams of H2O? So we have, again, this is one of the questions where it's super, super important. You cannot forget to do this. Our solute is the stuff that's being dissolved. That's 20 grams. Again, we were not given the solution. We have to find that. you're given the solvent, so the amount of water that was being used to dissolve it, which is 80. And we have to add those two up together to get our solution being 100. But again, only these numbers are part of our equation. So we get 20 over 100. So if you did 20 over, if you forgot to do this, if you did 20 over 80 times 10 to the 6th, you get a very different number. But 20 over 100 times 10 to the 6th gives us the 200,000, so 20,000. But again, our problem is that answer choice is not there. You could just kind of be like, oh, hey, well, it has to be that. There's no 5. But just so you're aware, 2.0. And then when you have a positive scientific notation, you're getting bigger. So you're moving your decimal point to the right. We're going to move it 5 times. So 1, 2, 3, 4, 5. That's how we got that. Now, that was it for this review video going over the quiz. Next time, we'll cover even more chemistry things.